Good morning, everyone. This is Esrat Jahan. I welcome you all to my presentation at the International Conference of Smart and Sustainable Built Environment 2024. My research paper is titled Optimizing Dynamic Facade Performance Through Parametric Design, a simulation-based strategy for improving daylighting and visual comfort in office buildings. I would like to start my presentation with a short overview of the topic. As many of you know, achieving a balance between energy efficiency and occupant well-being in the building design is one of the key challenges in modern architecture. Today, I'll represent how parametric design can be combined with advanced simulations tools like Ladybug and Climate Studio to improve building energy performance. Through a case study focused on Dhaka, my research explores how dynamic facade can enhance daylighting and visual comfort while reducing reliance on artificial lighting. I'll also discuss the broader implications of these findings for sustainable, energy-efficient architecture in rapidly urbanizing tropical environments. Let's begin by looking at the significance of this study. In rapidly urbanizing tropical regions like Dhaka, balancing energy efficiency and occupant comfort is a critical challenge. However, most studies focus on temperate climates, leaving tropical regions underexplored. My research addresses this gap by applying climatic design strategies to improve daylighting and visual comfort in office buildings, reducing reliance on artificial lighting. Using advanced simulation tools like Ladybug and Climate Studio, I'll demonstrate how dynamic facets can transform building performance, contributing to sustainable occupant-centered architecture in tropical climates. Aim and objective. The first objective of this research is to explore various design iterations while accounting for multiple climatic variables and their interdependencies. While the second one is to develop a comprehensive strategy for optimizing dynamic facade performance using parametric design on an existing building facade and assess improvements in building performance in terms of enhanced daylighting and visual comfort. The research methodology will be discussed here. First of all, the existing building conditions and environmental data were collected from field investigation. After that, using Rhino and Grasshopper and the input of environmental data, a 3D parametric facade design was developed. Then, using Ladybug and Climate Studio simulation software, the indoor performance of the climate-responsive facade was evaluated. At the end, the simulation results of the existing case and the modified case were compared in terms of daylight performance and visual comfort. Here we can see the list of the softwares that were used in this research. An existing administrative office building was selected as the base case. The tropical climate data were collected from the Energy Plus website. Well, it's a three-storied office building made of RCC structure and brick walls. It has mainly administrative office spaces, meeting rooms, research rooms, a library, and a computer lab. Using Ladybug plugin in Grasshopper, the existing condition of the building with surroundings was evaluated in terms of direct normal illuminance, wind speed, and relative humidity. Here we can see the annual solar radiation received by the building surfaces, where the maximum value is 1746 kilowatt per meter square and 174.62 kilowatt per meter square is the minimum value. This analysis helped to assess the energy potential for designing the climate-responsive facade. Here we can see a short overview of the wind flow analysis of the base case in respect with the site surrounding. The main problems identified in this building are insufficient daylighting that requires high energy consumption for the use of artificial lighting. The building form is elongated in east and west side that creates energy inefficiency. Overall, there is a lack of natural ventilation and the working environment is very. Here we can see the base model and the modified case model for this research, a specific space, computer lab, was selected, which is located at the second floor. For the climate-responsive parametric design of the building, repetitive cylindrical modules from the facade. The cylindrical modules work as a shading device that rotate horizontally at the east and west facade and rotate vertically at the north and south facade. The cylindrical modules can easily allow natural ventilation and daylight while cutting off the direct solar radiation. The rotation was controlled using the grasshopper script for Rhino based on the solar radiation gained by the respective facet. It was expected that the aluminum cladding modules would enhance the lighting penetration and improve indoor environment while maintaining or minimizing the direct solar radiation. Now I'll discuss the comparison analysis. The environmental performances of the base case model and the modified case model were analyzed using Clement Studio. Considering the key parameters, point in time illuminance, daylight availability, indoor glare, and visual comfort. First of all, I will discuss about the point in time illuminance. In Climate Studio, point in time illuminance indicates the calculation of illuminance distribution for daylight at specific moments in time. On the left side, we can see the illuminance distribution of the base case, where the mean value is 298 lakhs and the maximum value is 821 lakhs. On the right side, the illuminance distribution of the modified case is shown, where the mean value is 993 lakhs and the maximum value is 1965 lakhs. Comparing the both cases, we can see that daylight was improved in the modified case while enhancing the visual comfort and inviting indoor environment. The graph shows the daylight improvement for every grid bars is specified in the model. Now on to the daylight availability. Well, it means the sufficiency of daylight for carrying out work tasks and other indoor activities. In lit green building rating system, points can be gained based on the total spatial daylight autonomy, which is called SGA 300 by 50%, which signifies the proportion of floor areas that receive illuminance level of 300 lakhs solely through the 50% of the occupied hours. But on the left side of the base case model, the green color shows the daylit area and the gray one shows the non-daylit area. Overall, the daylight autonomy for this case is 23.3%. In contrast, for the modified case, the overall daylight autonomy is 95.7%. In this comparison, the spatial daylight autonomy for the modified case is larger than 75%, which qualifies for 3 credits in LEED Green Building Rating System. Now on to the annual sunlight exposure or ASC. It indicates the percentage of floor spaces receiving direct sunlight exceeding 1000 lakhs for more than 250 occupied hours, highlighting overlit areas, and the acceptable limit of AC is 10%. So on to the base case model, we can see the AC is 0.0%. In contrast, on the modified case model, the maximum AC is 2.2%. In this part, I will discuss about the annual glare. It is calculated based on the daylight glare probability or DGP metric. The metric has 4 bands, which are imperceptible glare, perceptible glare, disturbing glare, and intolerable glare. In the base case model, the value of DGP is 0.0%. In contrast, in the modified case model, the value of DGP is 6.5%. So, comparing the both cases, we can say the low levels of glare are often associated with reduced natural lighting. And overall, the dynamic rotation of the cylindrical modules effectively controls solar penetration and reduce glare, all while maintaining optimal daylight. In this part, I'll show how glare can be evaluated using a fisheye radiance rendering with an opening angle of 180 degrees for a specific view to perceive visual comfort for the occupant. The renderings were done for the 21st June, which is summer solstice, at 9:30 am, 12:30 pm, and 3:30 pm. It is also possible to determine luminance level of each bar seen in the radius rendering. For the base case, the point above the table has a luminance level of 54 candela per meter square, which increases to 278 candela per meter square in the modified case. Similarly, here we can see the radiance rendering of autumnal equinox, which is at the September 23. And this slide goes for the winter solstice, which is at the December 21. Finally, the radiance rendering for vernal equinox, which is for the March 20. Let's now move on to the discussion of the research findings. Contribution to sustainable architecture. This research fills a gap by focusing on facade design tailored for tropical climates, particularly Dhaka, Bangladesh. Most previous studies emphasize temperate regions, leaving tropical contexts underexplored. Parametric design for tropical regions. We applied parametric design strategies to enhance daylighting and visual comfort in tropical office buildings. Using advanced simulation tools like Ladybug and Climate Studio, we integrated local climate data, making the designs more regionally relevant and practical. Energy efficiency and occupant comfort. By reducing reliance on artificial lighting and mechanical cooling, the research promotes passive climate-responsive solutions. The approach strongly advocates for energy-efficient, occupant-centric building designs in tropical environments. Limitations and future research. While this study focused on Dhaka, its generalized may be limited, but it also did not address occupant behavior and energy efficiency comprehensively. Future research can expand on this by exploring other climates, building types, and integrating renewable energy solutions. Overall, the findings show the potential of parametric design for architects in rapidly urbanizing tropical regions, promoting sustainable and occupant-focused design. I'd like to acknowledge the support and facilities provided by Department of Architecture, Bangladesh University of Engineering and Technology. Thank you all for your patience.